development of civil engineering education in Indonesia. We believe in each of our steps that these values are the groundwork to reaching our vision of becoming Indonesia's most reliable civil engineering research center who can reinforce not just a sustainable but also an environmentally focused infrastructure. Seizing the cutting-edge era, the Department of Civil Engineering is supported with 6 adequate laboratories consisting of the Laboratory of Construction Management, Laboratory of Water Resources and Coastal Engineering, Laboratory of Transportation and Pavement Materials, Laboratory of Structure, Laboratory of Soil and Rock Mechanics, Laboratory of Concrete, Advanced Material and Computational Mechanics. The students can choose from 5 focus areas of expertise selected according to their interests. The Department of Civil Engineering is divided into undergraduate, international undergraduate, master's, and doctoral programs. Not just that, the department is also strengthened with 46 faculty members and 9 professors. With more than 6,000 library materials and various kinds of student activities, graduates from the Department of Civil Engineering have always a professional civil engineers. The department also builds a community through Aussits, so graduates can maintain a good relationship with one another. Furthermore, the Department of Civil Engineering will continue to bring forth many new generations to produce numerous innovations for the future of infrastructure development in the country. And that's all from us. If you want to know more about the Department of Civil Engineering, you can visit our website. See you around.
A life-changing history. Right. A solid mission of the visionaries. It was Dr. Anka and his colleagues making important roles in both local and global communities, ministers, CEOs, professors, entrepreneurs, and yes, another history maker. These successful alumni were trained in a healthy learning environment that was equipped with various supporting facilities. Vocation to marine technology. All faculties and departments of ITS were formed to be the best place to learn science, technology, and design. 7 faculties and 1 interdisciplinary school. Scientex, Faculty of Science and Data Analytics. MARTech, Faculty of Marine Technology. Faculty of Industrial Technology and Systems Engineering. Electics, Faculty of Intelligent Electrical and Informatics Technology. CivPlan, Faculty of Civil, Planning, and Geoengineering. CreaBiz, Faculty of Creative Design and Digital Business. Vocation, Faculty of Vocation, and Interdisciplinary School of Management and Technology. Recognized as one of the top best-ranked institutes doesn't mean the finish line for ITS. To gain greater international recognition, ITS launched International Undergraduate Program. Students can get wider international exposure through 20 study programs they can apply. The chances are also open for professors from all over the world to teach and conduct research at ITS. These opportunities have made international joint research and other international activities successfully performed. Like IUP, students and lecturers from other programs have also contributed to the ITS achievements. Appreciations earned exemplify Institute's excellent performance. But technology and academic excellence is not the only goal of the Institute. Students are guided to apply their knowledge for the welfare of society. Because to note a new life-changing history, technology must advance humanity. ITS, Institute Technology.
Nggak masuk.
Gadjah Mada, yang kami hormati Profesor Dr. Asih dari Institut Teknologi 10 Bandung, serta Bapak Ibu hadirin yang berbahagia. Pertama-tama, marilah kita panjatkan puji syukur kehadirat Tuhan Yang Maha Esa, karena atas berkah dan limpahannya kita dapat berkumpul di sini dalam keadaan sehat untuk mengikuti acara Seminar Nasional Manajemen Aset Infrastruktur dan Fasilitas serta International Conference of Infrastructure and Facility Asset Management tahun 2022 dengan tema Preservasi Jalan pada Kondisi Geoteknik Tanah Sulit sebagai Pengembangan Profesi Manajemen Aset yang diselenggarakan oleh Departemen Teknik Sipil, Fakultas Teknik Sipil Perencanaan Pertanian yang bekerja sama dengan Badan Pengelola Sumber Daya Manusia Kementerian PUPR. Izinkan saya, Adinda selaku MC hari ini akan membacakan susunan acara sebagai berikut. Acara akan dibuka dengan pembukaan, yang kemudian dilanjutkan dengan doa. Memasuki acara inti, yakni sesi pemaparan materi yang kemudian akan dipandu oleh moderator, dilanjutkan dengan isoma atau istirahat saat makan, kemudian dilanjutkan dengan memasuki acara inti sesi 2, kemudian ada presentasi publikasi sesi 1, akhir break, lanjutan presentasi publikasi sesi 2, dan penutupan acara yang akan ditutup oleh Bapak Insinyur Putu Artama Wiguna PhD selaku Kaprodi Pasca Sarjana Departemen Teknik Sipil, Fakultas Teknik Sipil Perencanaan Kebumian, Institut Teknologi 10 November. Baiklah, Bapak Ibu hadirin, sebelum memulai acara pada pagi hari ini, alangkah baiknya kita mulai dengan doa agar acara hari ini diberi kelancaran dan keberkahan. Doa menurut perasaan masing-masing, berdoa dipersilakan. Berdoa dapat dicukupkan. Baiklah, memasuki acara inti yakni pemaparan materi sesi pertama yang akan dipandu oleh moderator yakni Bapak Dr. Hitapria Suprayitno. Kepada Bapak Hitapria, moderator dipersilakan.
Assalamualaikum warahmatullahi wabarakatuh. First, I have to say good morning to Dr. Henning. Good morning, Dr. Henning. And from the all audience. Okay, we have strict time, so we have only 1 hour to discuss. First, I would like to introduce who is Dr. Henning. It is a bit interesting. He is a senior lecturer in University of Auckland in civil engineering. He is a founding member of Climate Adaptation Platform in New Zealand. He specializes in asset management, performance monitoring, and performance-based contract and benchmarking. He got his master engineering from South Africa, University of Pretoria in transportation, and then he goes to New Zealand, University of Auckland. He got his PhD from University of Auckland. He has experience in several wartime projects, especially in Philippines, South Africa, Indonesia, and around the Pacific, Vanuatu, Solomon Island, etc. That's the short biography I have. Mr. Dr. Henning. Dr. Henning, are you ready for your presentation, please? Ready? Okay, if you are ready, I will let you to present your presentation, please. Okay.
Thank you very much. Selamat pagi. Yes, Salamat. So I am quite familiar with Indonesia. I have done a project, a couple of projects. One was for the World Bank and one was for the ADB. That was mostly with the Department of Highways. So I know your country, I know your roads, and I've traveled on your roads. So it's really a privilege to be talking to you today. Just want to get the slide up. Sorry about that. Okay, can you just confirm that you're seeing my first slide? So today I will be talking about road asset management and really a little bit of a future focus into addressing the challenges for tomorrow. I am well aware that your topic is about road preservation in problematic soil conditions. I will not talk to detail about the roads in soil conditions, but really stand back and look at road asset management and see how we can use road asset management to have better roads over time and also to have more resilient roads over time. I'm also aware that Indonesia is in a part of the world that's very vulnerable to climate changes, also seismic activities. So certainly there's a good reason why we want to have our road network more resilient. So just starting at why this is important. Our road network is a backbone of our economic growth. And I think in particular with the situation in Indonesia, that is very important that we understand that our road network is a crucial part of making the country's economy stronger. Our infrastructure and our roads are also very important to the well-being of our communities. And what we mean by that is that all the socio-economic aspects is very important in our road network, to maintain our network, to make sure that we've got access, that our communities are connected, that people have got access to markets, to your ports, to schools and hospitals. And all of those things ensures that our community has got a better well-being. Also, I am aware that Indonesia has got some challenges around road safety, and certainly managing the road condition and our surfaces in particular is very important from a safety perspective. Infrastructure as such is also a very strong economic stimulant that the government uses to do certain things in a country. For example, if the government wants to create jobs and to stimulate the economy, it's a good place to invest into the road development, because that gives people jobs. Through their jobs and through their activities around infrastructure creation, there's a lot of onflow of economical activities. So it's important. So effective road management has got a significant part in the cost and the economic implications for a country. So I will be giving a little bit of an overview of fixed asset management, and particularly talking about the roads today. And my first key concept that I will bring across is that, and having worked in many countries around the world, I think often we've got a little bit of a disconnect between the accounting part within an organization and the engineering part within an organization. And hopefully through implementing road asset management, we will build that bridge between making the finances work on an engineering level also. First, looking a little bit about the benefits, the asset management benefits, and the figure in the right sort of summarized that in a little bit of a summary way. Now, there's the two top blocks there in that shape is all about more efficiency in our road network. That efficiency is made up by two parts. First of all, we get a better performance out of our network. So even if I invest the same level of money, my network will have a better condition over time if I use road asset management. Similarly, if I maintain the same condition, I can actually have some savings. So we normally find those two working together. So ultimately, I think that what it comes down to on the road network is that we are able to do more with the money. And have a better level of service to our community. What's then going to happen is we're going to have improved customer satisfaction and road safety. And then the second one there, something I'm going to spend a bit of time on today is also the resilience of our road network. So then on the right-hand side, I'm just highlighting some of the important one. I have spoken about effectiveness and efficiency, long-term sustainability for our communities, a more resilient network, resilient against seismic activities, against climate change, and other impacts, and then just adapting over time to the need of our road networks. Then also an aspect that I have come across also in the rest of the world, and this figure comes from IBM, and what it shows us is this asset management journey, and a big point that I want to make today is I am aware of some of the developments in road asset management in Indonesia. There's been some very good progress, but it is an ongoing process as we develop it. So we've been doing road asset management in New Zealand now since 1980, 85, and we're still learning and we're still improving over time. What we see there is how our practice or our asset management maturity improves over time. So on the left-hand side there is typically when I replace what's broken with exactly what was there in the past, and when all my maintenance is more reactive. Now, reactive is unplanned, so there's failures that I didn't anticipate. What we can see there in the blue, in the green line, is that is perhaps the most expensive way in which you can do maintenance. So as we start to do road asset management, my cost per kilometer of road maintained comes down. On the right-hand side, the blue line shows the performance and the reliability of my network is increasing. So over time, we need to do these improvements. What we can see here is when we start doing proactive, preventative maintenance, when we start using road asset management and road asset management software tools to help us with the planning, and with all of those improvements, I'm going to start seeing my cost comes down and my overall condition and level of service and resilience improving. Now this refers to the entire asset management system. I will be talking more about the system, and don't when we talk in the ISO 55000 terminology, when we refer to asset management system, that includes everything we do, from data collection, from the software that we use, the analysis software, the planning tools that we use, our maintenance contracts that we use. All of those includes the entire asset management system, and I will be talking more about that in the next few slides. So first of all, let's just see what we try to do here. And with road management, we have got a lot of pinch points, and as you can see there from the currency, this figure was borrowed from your neighbors from the Philippines. In an implementation that they are doing, and I'll talk more about that in a little bit later. When we do asset management, there's a few things that we need to look at. First of all, what is happening with our communities. And like the rest of the world, Indonesia has got a growing population. You've got a lot of urbanization taking place, so a lot of people from your rural areas and from your provinces is moving into the big cities, such as Jakarta. And we've got people starting to build in places where we need to build infrastructure. We've got our existing infrastructure that we have to maintain, and like the rest of the world, our infrastructure is deteriorating over time, so you have to invest into that. And then we've got these natural disasters from geohazards and from climate change and those sort of things. Now, we don't have enough money to cater for all of these things. No country has got enough money to cater for all these challenges that we have to do. So what we use our asset management system for is really to try and understand the investment that needs to go into addressing some of these things. How much should I be investing into new roads? How much should I be investing into my maintenance? And how much should I be investing into building a bit of a resilience, climate resilience or geohazard resilience into my network? Now, that talks mostly about the cost. So if you look at the blue arrows, you will see all the cost items that's coming in. But there's also the economic returns, right? So when I do road asset management and I invest in maintenance, over time, I'm going to start getting savings from that. When I invest in new roads, that costs me money, but building that new roads is going to stimulate the economy, and my economy is going to grow. When I invest in resilience, it costs me money to make things more resilient, but at the same time, I get savings in losses. So when there's an event, I don't get a total destruction of my road network, and the damage cost will come down. So with all of these things, we got to think of both sides. We got to think of the investment needs, but we also got to think of what the return on that investment will be. And the asset management process help us to make those decisions in a systematic manner. So just looking a little bit at the components of asset management, and I borrow this slide from one of my colleagues here in New Zealand, Ross Wall. What we have on the left-hand side would be the drivers in road asset management. So this is, first of all, level of service. So that is the condition of the road, how congested your roads are. The future demand, traffic growth due to population growth, urbanization, those factors. Physical risk on my network, and a good example of the physical risk is road safety. So the risk of vehicles being involved in a crash, and then sustainability and climate adaptation. So these are the drivers of our investment decisions. Now, we want to do the life cycle management of our roads and our road network, and we need to know what it costs. So the way that the system does it is, first of all, you've got to start with having the right information or data. So we've got to have all our inventory and condition data. It becomes the foundation of all of those processes. In life cycle management, what we try to do is to understand how much money should go into operation and maintenance, and how much should I be spending on the renewals and the new build construction. And having that balance right is quite important. From that, we will get the budgets and our financial forecast. So by doing it right, I just want to go to the next slide. By doing it right, what we will be able to do is to develop an asset management plan. And this is something I was involved with in the Philippines. They have rolled out, through technical assistance from the World Bank, the development of asset management plans across the entire country. So they've developed a national asset management plan, and they have started rolling it out at departmental level. So during our project in the past year, they have included their highways departments, their education, and their health sector. And all of those departments had to develop an asset management plan. Now, the asset management plan, you will see, have got a table of contents that is universally accepted around the world to look fairly similar. So we've got in that the introduction and the asset management practice that sets the scene of the department, your functionality, and some of the investment drivers. You then, chapter 4, will start looking at the condition and sort of the capacity demands on your network. Chapter 5 will talk about the level of service, and level of service for roads can be including the driver comfort, the roughness, your road safety, your congestion level, your traffic jams and your traffic flows. Chapter 6 is the life cycle management. So that talks about how much money I should invest into new infrastructure, how much should go into renewals and replacement, and how much into maintenance. Chapter 7 is sustainable planning. Chapter 8, natural hazards and resilience planning. I will talk more about that in coming slides. Chapter 9, the risk management. So that's physical risk management, excluding natural hazards. And then you get into your financial outcomes and the performance planning. So if there is a drive in Indonesia for adopting a formal asset management process, the end goal would be to develop the asset management plan. Typically, the planning horizon for such a plan would be thinking around the medium term. So you look up to 10 years investment and what the department want to achieve in the next 10 years. And then you will renew or revise the asset management plan either every second year or every third year. So it depends a little bit on your funding cycles within Indonesia. I do recall from my previous visits that Indonesia still have a very strong annual focus in the budgeting process. But I think what the asset management plan helps us doing is to get the budget allocations a little bit more streamlined so that you can have a longer term view on what your budget requirements would be. In New Zealand, typically we've got an asset management plan that covers a 3-year funding block. So when the government approves the funding, they approve it for 3 years. The problem that you have with an annual process that I have found in Indonesia in particular is that if there's a delay in the approval of funding, the time for you to actually do the road construction work that you ask budget for is too short. So you plan for 12 months, you get budget approval 2 months into the financial year, then you've got 10 months to deliver 12 months worth of work, and that often leads to underspending of our budgets. Okay, let's look at some of those in a little bit more detail. So the first one is looking at your demand. So what we want to see is what is happening with my population changes, how is my traffic changes over time, what is the capacity of my infrastructure. So this is really a big issue in some of your motorways and highways where it's under capacity, and what you need to do about that. And then also the future changes that will happen, such as city growth, or maybe future changes with getting in more public transport, or those sort of things. What is going to happen when you analyze those three things is you're going to come up with your infrastructure gap. So what do I need to change in the future, which will then ultimately result in my investment needs that I need to put into my road network. A quick one about life cycle management, and this is really the heartbeat of what we try to achieve with good road asset management. What we have here, and I'm first going to talk about the figure on the right-hand side. What we've got here is typically how a road pavement will deteriorate over time, starting at a very good, excellent condition, and then at the bottom, a failed condition. If I don't do any maintenance, my road is going to deteriorate over time. But what is important to see in this figure is that for 2/3 of the life cycle of a road, that road is in an excellent and a good condition. So for the first few years, that road is in a very good condition. then it starts to deteriorate. And as you see, when it starts to deteriorate very fast. So the cost of maintaining that road is increasing very quickly. So what we try to do with road asset management is actually doing early investment. And you can see here in my title, good infrastructure costs less, or good roads cost less. So if I keep my roads in a better condition, ultimately my ongoing cost on my road network is going to reduce significantly. Not only is the cost increasing as my roads deteriorate, there's certain things that happens as a consequence. So at some point, my customers going to start complaining. When there's potholes, when the road is getting rough, they're going to start complaining. When the roads deteriorate a little bit faster, then the safety becomes a problem. When you lose something like skid resistance, again, potholes, maybe wheel track rutting, water standing there, the vehicles have got crashes during rainy seasons. And then lastly, also, the more my roads deteriorate, the more vulnerable it becomes against climatic events. So my resilience reduced. So really what we try to do is to keep our roads in as good as possible condition. Now, when we use the software analysis, it helps us planning that. On the left-hand side there, you can just see what some of the decision drivers would be. And that gives us that we should invest, and when we do investment, we should think about the entire road network in a system. We got to try and reduce our total cost of ownership. And then when we do the analysis, we got to remember the customer health and safety and risk and resilience aspects when we do the analysis. Level of service, there's a few generic examples there of level of service, but I would like to mention some specifically related to roads. So accessibility, I think you're quite familiar with that, is just making sure that our road network connect to everywhere my community wants to go. In terms of the quantity and the quality, we want to make sure that our road network is in a good condition, an acceptable condition, and that we provide for the capacity on our road network. And I know that's a tremendous challenge in Indonesia. We want to make sure that our road network is reliable and also resilient against climate effects, and then that it's sustainable over time. So let's quickly look a little bit about the resilience aspects. So we've got three circles here. We've got, first of all, the disaster finance side of things in that yellow box. We've got risk management in the blue box, and a circle, and then we've got the asset management in the green circle. Those things cannot be separated. So what makes sense for us is to integrate some of my risk thinking and my financial consideration within my asset management process. So asset management, and this is what I have been doing quite a bit lately for the World Bank, is integrating climate adaptation into asset management, so that when we do the analysis, that we don't only fix our roads, but we actually also look at making them stronger against climatic events. And the process that we use for that is just, I'm going to go through that, so not too much detail, but on the top level there is the process we go through in the risk assessment. And then in the bottom figure itself, the way that we prioritize our resilient improvements. The top bit is all to do with my road network. So I want to know where the exposure, the risk exposure is, how fragile my network is, and fragility is how good condition my road network is. That will give my overall climate risk on my road network. And then at the bottom, my criticality aspects. So where do my people live? Where's the socio-economic aspects in consideration? For example, my road network going to ports, very important for economic development. Some areas around environment considerations, and then just a criticality. So lifelines is typically my routes that's used for evacuation and those sort of things. Understanding that criticality and the risk of my network specific links will then give me a priority rating between those for my investment planning. Right. So I hope I have convinced you that the road asset management is something important to do. What I would now like to stand still on is just how do we promote this within countries? So it needs to be led from higher level government to make sure that it happens. And I can give you some examples there in New Zealand. We've got the Treasury that's behind, they've got an infrastructure unit that makes sure that everybody, all the departments is doing asset management. We also got our Minister of Infrastructure and shares that portfolio with the Ministry of Finance. So finance and infrastructure coming from the same place. We also have the commission, the Infrastructure Commission, that looks at the country holistically. So that helps with thinking between, say, transport and education and health and so forth to make sure that we invest in the right things. In South Africa, we've got Treasury that created the City Support Program, and also they've got an infrastructure unit that is driving best practice in local government. So that is then rolled out in the different cities in South Africa. I've already spoken about the Philippines. So again, the Philippines budget department has created a technical working group that makes sure that asset management is happening across all the departments. So how can we then encourage asset management uptake? So you can do it through legislation. So you pass a law that asks for certain things. For example, in New Zealand, we've got the Local Government Act that specifies that all local or asset owners have to develop an asset management plan. And there's some requirements around that asset management plan. There could be national policies, government's policy statements that require asset management. It could be a funding application requirement. So that is linked now in New Zealand. The funding application process is linked to the Act. So basically what it says is that if you want to ask for money, you've got to have an asset management plan. And then obviously the leading agencies can also learn from each other and do better asset management. Excuse me. Also, when you do the development of asset management capabilities, it is not just software systems, and I want to warn you against that. The big things you need to look at is, number one, the people. Train your people, and this type of training you're doing here is very, very important. You've got to make sure that you've got the processes and integrated planning processes around road maintenance and resilience, and then have the right technology and tools to help you with that. And that includes my data collection, my database systems, and then my analysis systems that help me in doing asset management analysis. So the key messages is our road network is very important for the economy of our the socio-economic outcomes of a country. We are using public money, so we got to use it wisely and plan properly. We got to make sure that we establish the best practices in asset management, and that really needs to be driven from a central government level. And then we need to implement asset management capabilities over a number of years. And then I think that a point I've already made is that climate change is one of the things that we need to start bringing into our asset management process. So thank you very much for that. If you want to do the questions or if that's going to happen later, that's fine with me too. I also encourage people can use the chat box if they want to type a question. I believe that one of my students from Indonesia is also in the room and will be helping with translation if we need to do some translation. So Anissa, are you with us?
Tolong ada untuk partisipan namanya Anissa, tolong dimasukkan. Enggak, tapi dimunculkan di atas. We are trying to put Anissa in the screen now. That's Anissa. Anissa Hazara. Hello, Anissa Hazara. Okay, great.
Selamat, Anissa.
Okay.
Thank you.
Yeah. Okay. Good morning, students. Thank you.
I'm now recommended to her because from the same primary high school. Okay, that's the presentation from Dr. Henning. So if there's any questions from the audience here, please raise your hand. Or maybe you have something that you are not clear enough. You can post questions in narration. I will try to translate it into English. And there is also Ms. Anissa Hazana. Please help you also if you need. Yeah, Dr. Ria, please. Yeah, please stop.
Thank you very much, Theuns, for your online coming. I'm more than happy to have you in this mirror. And thank you very much also for Anissa Sana for helping us. I would like to know if we in Indonesia cannot provide with all the sectors that you mentioned, which is the most and the minimal system for this to asset management system can be helping us. This is the minimal system that can be helping us.
Okay. Very good. Very good question, Lisa. So, I want to encourage you to see this as a journey. So, as you say, you cannot start with the most sophisticated system when you're at the starting point. One of the first things you want to do is make sure that you capture all the data and the information. So implementing a strong database system will be an excellent starting point. And with that, the capability that you want to have with that is to be able to report on things. So you want to report on the asset base that you have. You want to report on your condition of different parts of the network. And in that in itself is already very strong information that's going to help you with the decision making. Once you've got that in place, then you can start looking at other systems to help you with the analysis, the risk analysis around resilience and those sort of things. But a very good starting point is having a database in place and having a performance reporting capability established.
Because then, thank you very much, but you know that in our system in Indonesia, there is in the remote areas that needs the simplest way to have this management. And you know that a lot and non-engineered infrastructures in here. What is your suggestion in that?
Okay, so absolutely, you are correct. There are parts of a country you cannot treat everything the same. So for the remote areas and the small areas, you got to have something very simple in place. The principle stays the same, so you still want your data and your information, but maybe at a small scale, having that in spreadsheets and a simple database would be sufficient. However, if you're with the Department of Works and Highways, they've got a far more complex network, a significant network, so you would expect their systems and their software systems to be a little bit more sophisticated. So you do find we've got a saying in New Zealand that your process got to be fit for purpose. So if you're small, remote, something simple is good. If you're large, complex, you need more sophistication. I hope that answered your question.
Yes, thank you.
Okay, is there any questions from the audience, please?
Thank you, Chef, for the time. My name is Diki. Professor Henning, I don't have a clear understand on the graph about road section H and pavement condition on slide 11. We can see on that graph on slide 11 that we have 6 pavement condition, and then in the fair condition we can see there are two projects to resurface the pavement condition, but the first resurface it only changes the graph, not to increase the condition like the second resurface. Can you explain it more detail, please? Thank you.
Okay, I just want to congratulate you. Your sense of observation is absolutely immaculate. Yeah. So, what you're going to find is that when your road is in a very good condition, there's no cracks, there's no potholes. When you do a resurface, you don't necessarily get a condition improvement. So your road has to deteriorate a little bit when your resurface will start improving the condition, right? So you it depends on what you want to do and when you want to do it, but your ultimate goal would be to keep, with preservation treatments, your road network in as good as possible condition. Because when it then starts to deteriorate, and in your case where you've got a lot of asphalt roads and concrete roads, initially you may get away with just an overlay, maybe not a thick overlay, but if you don't then invest that money, then your road will deteriorate fast, and then you would look at rebuilding your road, which then cost a lot of extra money. Yeah, so the earlier we intervene, you're not necessarily going to get a condition improvement like we do have there, but the aim is really to keep my roads in that very good condition. A very good question and good sense of observation there also. Thank you for that.
Is the question is answered? Well answered, I think. Or any questions anymore? Please.
Yes, I understand.
Yeah, yes, that's right. Okay, any other questions, please, from the audience here? We still have enough time to question and answer, so please profit it. No. Okay. I give occasion for the online audience. Is there any online audience who want to ask questions to Dr. Henning, please? There is no audience, online audience who wants to ask questions, please. No? Dr. Ria again, please, so Dr. Ria.
Thank you very much. In terms of research, what do you have research ongoing, or what is the project that will be interested you in Indonesia? Because we would like to have a collaboration if it is possible.
Yep. Thank you very much for that, and certainly I'm always open to look at research in other parts of the world. I was quite privileged this year having my students in all different parts of the world. My research interest at this point in time is looking at climate resilient technologies. So, and also in terms of carbon footprint technologies. So what are some of the technology changes that we want to do that's going to make our roads last longer, and especially the surface, because that asphalt part, that's the most expensive part of our road pavement. What can we do with the technology to make it last longer? What can we do with technology to make my roads more resilient against flooding events and those sort of things? And then also, what should we be looking at to reduce the carbon emission as a result of road maintenance and rehabilitation? So those are the areas that I'm very interested in. My previous work that I have done in Indonesia was focused around performance-based contracts. I still have an interest in that. And then I guess anything that relates to the asset management area that includes data collection. So my student Anissa Sana, she's helping me with looking at a project where you get a vehicle that does laser scanning of the road surface, And then from that, the computers got AI or artificial intelligence to interpret the scanning image and come up with where potholes are, how much cracks you have, and so forth. So all of those things that's part of road management is certainly in an area of interest, but my primary focus is around climate resilient roads, and also making sure that we've got reduced carbon footprint with our road infrastructure.
Yeah, because now we are in Indonesia, the government encouraged us to use the waste materials for pavement.
Yep.
Yeah. For pavement like fly ash, bottom ash, and also the reclaimed asphalt pavement.
Yeah.
Was encouraged by, was and is still encouraging by the government.
That's right.
Yeah.
So I mean, recycling asphalt is an obvious one, especially for Indonesia, because you are using quite a bit of the deep lift asphalts. And the recycling technology is now getting well understood. So I think there's definitely potential in that. Using reclaimed materials in road construction, I fully encourage that also. In particular, you do have quite a few old concrete pavements. And I think when you rebuild that or demolish the concrete structures from buildings or from bridges or from roads, that makes very good road building materials. Your melter slag is a good surfacing material because it's quite hard and it's got very good skid resistance. The other material that we have done some work in New Zealand looks at the use of recycled glass. So when you mill up glass, you can use that in your pavement. So there are some good ideas. I think the one thing that we got to remember all the time, and especially with the waste materials into roads, is sometimes you can get the waste material in the road and it works, but your problems start when you have to rebuild the road. And you cannot use that waste material again.
Yes.
And then you may have a problem. So don't think of just what you do now. Also think of what you need to do in the future when you look at that. So when you do look at the research, is don't only look at the construction and the performance, but also think a little bit about when that breaks, how you're going to maintain that in the future, or how you're going to rebuild that in the future.
Yeah. Since natural resources is becoming less and less, even we try to have the artificial aggregate.
Yep.
But the problem is that the durability and the stiffness cannot compete the natural one.
The natural aggregates. No, absolutely. I think that's Indonesia is not as much in trouble as New Zealand. So, for example, we use quite a bit of the thin surfacings in New Zealand, chip seals, so not asphalt, chip seals. So you spray bitumen and you put aggregate on top. Mm-hmm. And we've got problems with the supply of the chips that give us the required skid resistance. So I think that's around the world the problem where our natural resources is getting depleted. And we got to think about that in the future. We got to think about artificial replacements. And again, we have done quite a bit of work in crushed concrete to use that in road construction, and it just makes sense because it is a strong material. What you've got to look at in particular with your research is understand the performance of the artificial materials, because if you've got a material that's variable, it then becomes very difficult in your specification and design of your road if you don't know how it's going to perform. So you look for something that's is quite consistent with its performance. And again, concrete is a good example of consistent. We know that broken glass, that's consistent, but sometimes you get mixed materials that is, you're not too sure what the performance is going to be.
Thank you very much for a fruitful discussion. Then the time is for the moderator.
Any questions from the online audience, please? The online auditions. Are there any questions from you all? We still have time, a lot of time.
Not really.
No, it's, oh yes, definitely. Any questions? So I ask my questions, please. In Australia, in New Zealand, what is the segment of road? What is the typical different kind of segment? It's asphalt segment of road. What is the typical maintenance we do and how much? And again, another question: what is the comparison between the South? Because we do little research here for Institute of Public Works of schooling, the investment costs. Excuse me. The investment cost is the same as the 10 years maintenance cost. So how about this for the road in New Zealand?
So I have to say that the road network and New Zealand as a country is very, very different to Indonesia.
Right.
Is New Zealand, and you must remember, so I came from South Africa and I've been all around the world. New Zealand is very small and we don't have many people. There's 1.8 million people in Auckland, which is our largest population area, but the total country has got 4 million people. So we've got light traffic. So therefore we use thin natural aggregate pavements with a thin surface on top. We do very strict overloading control, so our vehicles are not as heavy as in Indonesia. We've had a good look at Indonesia and the overloads of your trucks, because you know in Indonesia I've seen they load a truck until the wheels break off, right? So your trucks are very heavy; they cause a lot of damage to your road pavements. You've got thick pavements, structural asphalt pavements, concrete pavements. And you're absolutely right. They do require a lot of maintenance, and the maintenance cost is high. In New Zealand, typically we would get around between 20 to 40 years out of a road pavement. And in that time, we would say that 20% of the cost will be the initial construction cost, and 80% of the cost goes into maintenance. But what you've got to remember, what we do in New Zealand is we do a lot of road maintenance, a lot of resurfacing. So we would typically resurface any road between every 8 to 12 years. It will get a new surface. So our maintenance and the renewals is ongoing and quite intensive. Whereas the type of pavements that you built in Indonesia is very strong, and they tend to last a little bit longer. But again, with the heavy traffic, you will have a high maintenance cost going in on your road network.
Thank you very much. Yeah, it's very different, of course. Yeah.
Yeah.
Resurface for Indonesia, maybe 5 years. You have to resurface again. In New Zealand, is that?
Yeah, you can resurface 8 to 12 years. You will have a new resurface. Some 5 years. You're right. Yes, depends. Yeah.
Okay.
And the other thing is, I think that the one thing we do have in common with Indonesia is you've got a young geology. So you've got very sensitive soils, and the same in New Zealand. So we don't have the strong continental aggregates, that you get in the likes of Australia or in Europe. Old, geologically old formations. Our formations, due to volcanic action, it's relatively young. And it's quite a lot of clay and problem soils that you have. Now that is the same in New Zealand. We're similar in that sense.
Yeah. Okay. Anyway, time is up. So we'll close. Thank you very much, Dr. Henning, on the fruitful.
Terima kasih.
Thank you very much. I hope that we can discuss again someday in the future. Thank you very much. So the time is up. Now I give the occasion to the Pastor ceremony again. Please.
Thank you very much, Theuns, for everything that you have done for us.
You're welcome. I also thank you for the opportunity.
Okay. We hope that we can collaborate anyway.
Baik, thank you Profesor Henning dan terima kasih Bapak Hitapria. Selanjutnya akan ada pemaparan materi sesi 2, namun sebelum itu bagi peserta yang offline dipersilakan untuk mengambil coffee break sebentar dan bisa segera kembali dikarenakan materi akan segera berlanjut. Untuk pemaparan materi selanjutnya akan diberikan kepada moderator, kepada Bapak Dr. Trihanin Dioren Disatria. Waktu dan tempat saya persilakan.
Ini apa ini nggak dipakai?
Nggak gelem, sob.
Good afternoon, Sensei. I think
yes.
Professor Toshifumi Mukunoki is already here.
Okay.
How are you, Sensei?
Good morning.
Good morning. But I think afternoon in Japan.
Just before noon. Yeah, almost. Konnichiwa. Yes, afternoon. Good afternoon. Almost.
Konnichiwa. How's the weather in Kumamoto, Sensei? How's the weather?
Yesterday is worse. It's now Kumamoto is a rainy season. So we are afraid something happened. No way, but who knows? Now
but I think I'm looking forward to go there again.
Yeah.
Okay. Actually, Mahendra is also here, Sensei, to help managing the seminar. Mahendra-san. So, I think it's time for me to start the seminar. Please let me start the seminar, Sensei.
Sure.
All right. Good morning, everyone. Both in online Zoom and also in the meeting room. And good morning for Professor Toshifumi Mukunoki. Welcome to the second session of today's webinar. I will facilitate this session that is scheduled to be finished at 10:30 a.m. in Indonesian time or 12:30 a.m. in Japanese time. And first of all, I would like to greet Professor Mukunoki. It is such a great pleasure to have Professor Mukunoki as one of the invited speakers in today's agenda. Professor Mukunoki actually was the academic supervisor of Pak Mahendra and me. Together, he supervised with Professor Asih and Professor Endra during our doctoral study in Kumamoto University. Thank you so much for your supervision and support, Sensei. All right. Before we start the session, I will read briefly the CV of Professor Mukunoki. Professor Toshifumi Mukunoki is a professor in Faculty of Advanced Science and Technology, Kumamoto University. He graduated from Kumamoto University in 2001, and the topic of his PhD degree was Evaluation the Failure Mechanism of Soil Materials using X-ray Computed Tomography, CT scanner. And his postdoctoral supervised by Prof. Kerry Rowe. And he is also the member of Earth Member Laboratory. And for the collaborations, several professors already joined with him. Professor Andy in Canada, Professor Lauren, Professor Patrice Delmas, Professor Annie Julie, Dr. Matthias Halis, and of course, Professor Ria Sumitro in ITS. Dr. Hoai Vietnam and Professor Yoshi Sisa in National Defense Academy. All right, Sensei, I would like to also inform this session that will be divided into two parts. The first part is the presentation with time duration of 30 until 40 minutes. Afterward, we continue with the Q&A session for 20 minutes. And then without further ado, please, Sensei, the time is yours.
Okay, thank you very much for your very kind introductions. So my name is Toshifumi Mukunoki from Kumamoto Universities. And I also would like to thank you very much to the Dr. Ria because she invited me this good conference. So anyway, now Dr. Satoria introduced me about my research background, but today I'm going to different topics because my main topics was the more other geo-environmental, like soil contamination by the oil, but today is not like that. So I would like to talk about the study on the shear strength reduction characteristics of volcanic earth soil using XSCT method. I would like to share my screen from now. Oops. Sorry. Now, can you see my screen?
Yes, it's very clear.
Okay. So, I think before I would like to talk about my presentation, where is Kumamoto? Do you know that? I don't think so. Mostly Kumamoto is not famous yet. So the beginning, I would like to talk about where is Kumamoto. So this is just the map of the Asian region. So the green part is Indonesia, and the orange part is Japan, as you know. Japan made 4 islands. So the Hokkaido, Honshu is the main island, and the Shikoku, the small one, and this is the Kyushu. So the Kyushu exists in the west part of Japan. Okay. Then, so Kumamoto, this is the Kyushu. The Kumamoto is the center of the Kyushu. So Kumamoto is here. So after the 2016 and 15, I forgot. And Dr. Saturia and Dr. Maulana, they were here as a double degree student between the Kumamoto University and the ITS. Then Kumamoto has RGB properties. What do you mean the RGB? R means, so Kumamoto has a volcano. It's like, and also we have lots of mountains. So that's why I'm gonna say the green. Then Kumamoto also has a sea, rivers, and groundwater. So groundwater is also very famous in here. So I would like to say Kumamoto has RGB properties. If I say so, the Surabaya and Kumamoto may be very similar each other from the viewpoint of the geology and the geotechnical engineering. So we may be able to share the experience of geotechnical studies, I think. That's why I and Dr. Ria had collaborations, I think. Okay, so this is a brief introduction. And before, I forgot one more slide. So when you have time, I would like to encourage to access our website about the XR centers. So the XR center has the 3 different types of the X-ray computed tomography scanners. I think that you know the X-ray CT scanner. When you got the sick or you got the injured, when you go to the hospital, if the situation is serious, I think the medical doctor will check your body by using the X-ray CT scanners. So X-ray CT scanner is the non-destructive testing method to check the human body, basically. But in our case, the target is not the human body, of course. The target is the soil, rock, concrete, like that. So we have an industrial type of the X-ray CT scanner. That's why today I would like to share the X-ray CT image using these scanners. Okay, so now today I prepared these contents. So firstly, I would like to talk about the research background. Okay, so it is called from the Kumamoto earthquake. Kumamoto earthquake happened the April 14th and 16th in 2016. So at the time, the seismic level is more than 7. It's pretty big already. However, after 28 hours later, we get a bigger shock. So that's why the government changed the name. The 14th one is foreshock. 16th one is called main shock. So anyway, the Kumamoto earthquake give lots of damage to the Kumamoto downtown area and the mountainside areas. If you are interested in these topics, so you can access to my papers to the sources and foundations. So this is the open access. So later you can download it. As long as you just search the Kumamoto earthquake and my name, I think you will reach this paper. Okay. Before that, I have to apologize. In my slide, I remain some Japanese. I'm sorry about that, but not so important. Anyway, so this is the seismic intensity distributions. Orange line means the downtown. The blue line means the mountain areas. So look at this. The orange line case, it more than 1,000 gar. So it's a very huge earthquake. So this one get the April 16th in the very midnight. Actually, after the foreshock, the people evacuate each areas. Then, after 24 hours later, people start to feel, maybe situation is calmed down. We can go back to the house. But that was bad ideas. just 28 hours later, the bigger one came. Then unfortunately, some people were died. So that was very scary one. Then also, this is not only once. So after that, so not bigger like that, but a relatively big one came repeatedly. So that is also the feature of Kumamoto earthquake. So this is the geology map of the geology map of the Kumamoto cities. As I said, Kumamoto has the active volcanoes. So some volcanic ash soil is transferred by the big rivers. So that's why near the bay, there are lots of the soft soil. Then on the other hand, in the mountain side, there are lots of the volcanic ash soil. Because of these geological conditions, we have many damages by the liquefaction or slope failures, especially the downtown area. There are lots of liquefaction damage. And also, this one is the fault. And this is the foreshock caused by this fault. Then main shock caused by this bigger, longer fault. Then here is the town name is Mashiki. So Mashiki exists very central of the two faults. That's why, excuse me, the Mashiki area really damaged. Yeah. But today I would like to talk about more the mountain side. Okay, so this is just earthquake level distribution by foreshock. So anyway, the April 14th, as I said, the Mashiki is here. So the Mashiki area is almost the maximum seismic level. The intensity it's 7. But after main shock, that distribution is really distributed. It's expanded. You know, here is a mountain area. At the foreshock, not so damaged. But after main shock, the seismic intensity is pretty extended. So that's why in the mountain area, we observe the many slope failures. So this is the situations. Then today, I don't have time to explain everything. Just I'm going to focus about the landslide. But you know, because of the main shock, the mountain area distributed in volcanic rock, volcanic soil, and debris soil. That's why we could observe almost all type of collapse form. It's like a rockfall, toppling, bedrock collapse, and the catastrophic collapse, surface collapse, and the continuous surface collapse, the landslide, and debris flows. Today, I'm going to focus about the landslide. Okay. Then, when you imagine the landslide, how is that? It's a quick behavior or slow behavior. How do you think? If I were there, I'm asking the student, raise your hand. But this is the difficult situation. So anyway, I'm going to ask you to imagine the landslide. Oh, by the way, the students are mostly the civil engineering students. Maybe not.
Yes, since it's from postgraduate students.
Okay, so I believe that mostly people know the landslide. Okay, when I talk about the landslide, sometimes I'm using these examples. Okay, you know, this is now the glass tower on the tablecloth. When you pull the tablecloth quickly, what happened? Probably you get a success. Success means the glass tower does not fail, collapse, right? But if you pull slowly, what happened? I think you have you can imagine the two situations. One is, yes, glass tower is collapse, right? Because the glass tower lost the balance. But if this lady pulled the tablecloth nicely with slowly, probably the glass tower can keep these the conditions. So landslide is like that. So partially the soil is really shared. Then surface soil is still same. That is landslide, I think. But today's landslide is, I think, the mixed conditions. Some part is quickly move, and some part is slowly move. Okay, so this is a picture taken from the helicopters. Actually, not me. The Professor Yasufuku from the Kyushu University, he had a chance to take a picture from the helicopters. Then, so this is the situations. This is the observation laboratory of the Kyoto University to observe the volcano, actually. Then this slope is pretty gentle. The slope degree is 10 to 15 degree. When slope the inclination of the slope is more than 30. It's a very steep slope. But this is the 10 to 15 degree. It's very gentle, very not steep slope. That's why there are some community here, because the people never imagined this kind of the situation happened. But unfortunately, at the Kumamoto earthquake, the many soil attacked to this community, so that some people were dead. This is a bad story, actually. But then you can see some soil, but you also can see some green as well. This green is actually before the earthquake. It's like that. So do you understand what I want to say? This glass is like a glass tower. So some green is still can keep, then move because of the landslide. So this is what I want to say. I hope you can get my point. Then, so this is the pictures from the bottom part of the landslide. Actually, it was taken after the main shock. This picture is also not me, from the Kyushu University, Professor Kasama. Then, this is the observatory laboratory of the Kyoto Universities. Then now, people start to reach this cliff. Okay. Then this cliff is here. Okay. So when you see these pictures, you can recognize there are some schemes. So this is strictly speaking, color is the brown, but in Japanese we called akaboku. Aka means red, boku means clay. So this is a kind of a red clay, but component is the volcanic clay. Okay, and then the black layer is the kuroboku. So kuro means black. So this is also black volcanic clay. But why black is because the black layer involves more of the organic matters. So in our area, we can see this kind of the situations. But because of volcanic soil, this landslide happened. It was not. We observed another interesting layer. These people try to check these pictures. You can see the orange layer. What is that? This orange layer is pumice. And I believe you understand the pumice. Pumice means more of a porous rock. Am I correct? I think pumice is a porous rock, but the rock is not that big, like soil materials, like soil particles. Then that soil particle has the very porous because of the volcanic ash. Okay. Then we just discovered these layers. Then another point is this layer is not so large, not so thick. It's very thin, like almost 10 centimeters, like this. Partially the 20 centimeters, but mainly the almost 10 to 20 centimeters. So this caused some problems. And also this the gray layer is a hard clay, very hard clay. Now, this is the kind of the plain view. The pumice soil is like a sandy soil, like a clay soil. It's very difficult to recognize when we see these soils. Okay. So anyway, the situation is the volcanic pumice just sandwiched by the hard clays. So this is the situations. Then, so this is the kind of the plain view of the pumice layers. I think because of the landsliding and overburden pressure is pushed the pumice layers, then the pumice layer stick onto the hard clay. It's like a cosmias. Then I think we observe some crushed pumice layers on the hard clay. I hope you can imagine what's going on. Okay. Then observation summaries. So volcanic soil, which are often found in the mountain area in Atoll, undergoes changes in their internal structure due to the shear, which reduce their shear strength. As a result, there is a risk of the causing disaster such as slope failure. As one of the example, large landslide failure, and this area is called Takanodai. Large landslide failure in Takanodai district, Aso City, Kumamoto, Japan. The picture is here. Then the gentle slope, as I said, it's almost the 10 to 15 degree. The cause is the thinly distributed the pumice volcanic soil. So then, despite the gentle slope, the surrounding area is heavily involved. So that was our interest. So then, this is the XCT image of the pumice rock, pumice particles. You know, the pumice particle should be very brittle. It's like a particle breakage happened. And also, some water can exist in this porous part. When you see the XCT image, black part is the low density part, white part is the high density part. So in this case, black part means void. And the white area means like minerals. Okay, so I observe some water in the porous part. That's why, and there should be excessive pressure also exists in the particles. Then after the earthquake, the reduction of the shear strength happened. So this is the kind of the stories, but this is still a story. So we need to evaluate what's going on. But you know, the situation happened always inside. That's why we need to use X-ray CT scanners. So the objective of this study is the effect of the fracture characteristics of a volcanic pumice on its own shear strength is evaluated using X-ray CT to investigate the cause of landslide. So in this presentation, I would like to focus about the single particle breakage test and direct shear test under constant pressure and using X-ray CTs. So in case of the single particle breakage test, I didn't use the X-ray CT, just using this camera. But for the direct shear test, we need to observe the inside. That's why we use the X-ray CT. Okay. Oh, I have to accelerate my presentations. So I would like to show the physical property of the volcanic soil. Okay, this is the akaboku. This is the first layer. The kuroboku is the black layer. Then the volcanic pumice is this one. Okay, and this is the moisture contents. So the red akaboku volcanic soil, volcanic clay, black volcanic clay has very high moisture contents. When we see the volcanic clay, it was not like that. But when check the moisture contents, we see, oh my God, there are lots of the moisture contents. On the other hand, the volcanic pumice, not so high. And also, when we check the consistency, you know, in case of the volcanic pumice, no plasticity. So this means the volcanic pumice is a sandy soil. It's very difficult. Maybe not completely sandy soil, but maybe not completely clay. It's a very intermediate conditions. Okay. Then when I also check the distribution, particle distribution curve, so this is the result. See, when this is completely gray, we see more fine parts. So this distribution curve is like a sandy soil. Then this is just a picture. Okay, so this is the general information. Okay, so this is just a picture of the one particle of pumice. You know, you can see some porous part. So this is the fine soil is filled with the pore of particles. You can imagine. I hope. Then inside, what happened? When I scan these particles, you can see this kind of the image. It's like a sponges. You know, the white part is a matrix part, while the black part is a pore part. This white area is like minerals. Okay, so this particle inside of this particle is like a sponges. So, and this white part is relatively hard. So you know, when we apply the load, until the limitation of the strength, somehow the particle can keep. But once over the maximum strength, this is the really sponges. That's why they're crushed immediately. So this is the pumice. Okay. Then after image analysis, so we can evaluate how much the porous area. So like that, we can do that. Please remember, X-ray CT image is not like a microscope image. X-ray CT image is the digital image. That's why we can apply the image processing or image analysis. So this is the point, okay? Then this is a 3D image. So we can observe how the porous condition is distributed in one particles. So this is the advantage of using the X-ray CT scanners. Okay, it's like a cheese. Don't you think so? Okay, then we apply the single particle breakage test. Oh, I have to start. You know that the test apparatus is simple. So this is the specimen table. Just we place on the particle, and then we apply the load. Then just we check the load and displacement. So test is very simple. Okay. Then the loading speed is 0.1 millimeter per minute. Then you know, we can take a picture of the one particles. Then this is the when we took the pictures, it should be 2 dimensions, right? Because the pictures. So anyway, somehow we would like to evaluate the roundness of the one particles. You know, roundness means like a sphere element or very complicated. So likewise, I would like to evaluate the particle shape quantitatively. So this is just the equations. As long as we know the area and as long as we know the perimeters from the image, we can calculate the roundness. Then later we summarize the data. Okay, and also of course we apply the load, so we can check the load and displacement. But you know, if the particle is really how can I say dense, the particle should be like broken, like 2 parts, right? But this is a pumice, so should be like very complex. So I think that the compression load and displacement behavior, it should be different. So this is also the evaluation point. So you know, the peak is not once. Probably sometimes we can observe the peak load. So that is also our the observation point. Okay, let's see the results. In this test, we prepare this is a pumice. So this is a granite soil, and this is a core. Is this correct? Coral sand from the sea. Do you understand my point? Coral sand from the sea. Okay. So then we compare these particles. Then what's happened? Then you can see some minimum load and the maximum load. So when in case of the PARMIS, the maximum load is the 219, but the minimum load is 8.7. It's quite variable. Then a decomposed granite is the maximum is less than PARMIS. Oh, this is interesting. And the coral sand is harder than PARMIS. The Kesa means like silica sand. Silica sand is the most hard. And also we apply the glass beads. Glass beads also hard materials. Okay. And then roundness. This roundness, and also the roundness of the variations. So the glass beads is spheres. That's why the value is 1. The other is not spheres, but there are some shape. Oh, I'm sorry. Then the vertical axis means the strength of the particle breakage. So the slight negative relationship between roundness and the single part crushing strength is observed from these pictures. So angularity, rough surface particles are relatively fragile, I think. So this is one of the observation points. Okay, and also the rupture crushing, the crumbling crushing, we observed. We're gonna say the two patterns. So in case of the crushing pattern is A, and when we crushing load is large, the crushing form is like A. So that means, the glass beads or the Kesa, when broken, it's like that. But granite soil or PARMIS, and it's like that. So the crushing form is different. It's like this. So we need to imagine that this kind of the situation happen inside of the ground. Then what's happened, right? So this is a crash after the coral sand. So quite different. Of course, this is only the single compression test. The situation is in the soil. So we need to think about this totally. Okay. What time? Oh, after 20. Then this is the summary of the relationship between load and displacement for all samples. So each sample has the peaks sometimes, and then the peak is almost constant. The fracture is brittle. In case the constant crushing strength, this means exists in the extremely heterogeneous structure in the particles. So this is the situation, especially this one. It's quite repeated. Repeatedly, we can observe the peak load. So I think each particle has a very heterogeneous conditions. Okay, then let's move on to the direct shear test for X-ray CT. You know the direct shear test. There are two kinds of the direct shear test. One is the constant pressure. The other is the constant volume. And here we don't have the constant volume test apparatus. Just we have the constant pressure. Actually, we newly developed the direct shear test apparatus for X-ray CT scanners. That's why somehow we could observe inside of the specimen of the direct shear test. Okay. Then somehow we installed the direct shear test apparatus inside of the X-ray CT room, and then we can perform the almost same test as a conventional test. Okay. I would like to skip the detail about the test conditions of the CT scanners. Anyway, we applied the reasonable conditions. Okay, so this is the shear test the constant pressure procedures. So initially, we need to check the initial conditions. So 1, 2, 3, 4, 5 means the scan point. So we observe the initial conditions. Then we applied the 0.3 millimeter displacement and then stop. Then we can scan. Then we apply the 3 millimeters. Then we stop the share. Then we scan. 5 millimeter, scanned. In the end, we scanned. So for this test, we scanned 5 times during the direct share test. You understand the process? Okay. Then after share test, we evaluate the reduction rate of the share strength. So from the direct share test, we can observe the share behavior. So evaluation of the share strength, evaluation of the share strength reductions. Then we compare with the particle properties. So this means we prepare the sample based on the pumice, coral, and the granite soil, and silica sand. Then we can compare what's happened. Okay, and then also we evaluate the vertical displacement, of course, because this is the constant pressure test. Then we visualize the internal structures. As I said before, because this is the digital image, so somehow we can evaluate the shear strain distributions using digital image correlation. This is the typical image analysis method. So I don't have much time to explain detail about the digital image correlation. If you are interested, you can take my paper later. Okay, so let's move on to the result of the direct share test. So before we apply the direct share test, of course, we apply the consolidation process. You know, just I'm gonna say the data. So CC is the compression curve. It was 0.536. This is a relatively larger than conventional clay. You know, the blue line is the conventional clay. The yellow curve is the pumice. So look at this. The slope is different. In case of the pumice, it's a much more steeper. So this means once the pumice soil get the yield stress, immediately the pumice soil lose the porous conditions. That's why the really compressed. So this is the feature of the volcanic pumice, I think. Then, when we apply the shear stress, what's happened? The orange line means the sample has a wet conditions. The purple means dry conditions. Honestly speaking, I forgot how much wet. I'm sorry about this. Anyway, so this is the shear stress and the horizontal displacement. And on the other hand, so this is the vertical displacement and the horizontal displacement. So look at this. There is no positive dilatances. Even though the density condition is the pretty dense conditions, you know, we don't see the positive dilatances. So this is the kinds of the feature of this sample. Okay. Then from now, I'm going to show you some CT images. So that this one is the wet pumice soil, dry pumice soil. This is the silica soil. Okay. Then this image is after 8 millimeters. So we can observe some particle is like a rotate or move. So this is as a first observations. Okay. So the rotation and rearrangement of the particles due to shear in the pumice and the silica sand during the wet, during the sharing, okay? Then, when we apply the digital image correlations, what's happened? I'm gonna repeat the digital image correlations. So, you know, when you see the original CT image, we cannot observe any strain. Just we can see the density distributions. But when we apply the image analysis, you can observe this kind of the data. So now this one is the shear distribution of the shear strain. Okay. So just this is the visualization of the shear strain of pumice by digital image correlations at initial to 0.3 millimeter displacement, from 3 millimeter displacement to 3 millimeter, 3 millimeter to 5 millimeter, 5 millimeter to 8 millimeters. So, when you see the original image, you cannot see the big difference. But when you see the result of the DIC means digital image correlation, we can observe some shear strain distributions. So this is our new discoveries. Okay. So the shear zone develops on the lip until peak shear. Initially no shear strain, of course, but due to the shear stress, the situation is like a lip. After yield stress, shear zone becomes very thin, very thin. Okay, then now I would like to compare the other soils, like decomposed soil, coral sand, and silica sand. Then in case of the decomposed soil and coral sand, we can observe some positive dilatancies. Okay, but for the pumice soil, it's negative dilatancies. Then I'm going to show you the same results. And the decomposed soil, coral sand, and silica sand show the decrease in dilatancy due to the positive dilatancy near shears. So this is the first observations. Okay, so this is the decomposed soil. So this is the silica. So this is the coral sand. Okay. Then when we apply, this is the last stage. So this is the pumice soil. So this is the decomposed granite. This is the coral sand, the silica sand. Curved shear zone were observed in the descending pumice, and straight shear zone were observed in decomposed soil, coral sand, and silica sand. And also, when you check the thickness of the shear stress, I think silica sand and coral sand is thicker than the pumice sand. Why this has happened? Because due to the shearing, the silica and coral sand never crushing. Somehow, particle is on the particles. But during the shearing for the pumice, I think the pumice particle cannot hold the particle. The one particle crushing. It's crushing. That's why the shear strain distribution situation is different. So this is our observations. And also, almost time, right? Yeah, almost time. So I just check the reduction rate of the shear strength and the average particle breakage. Just we check that, but there is no clear correlation between the rate of the shear strength reduction and the single part strength. And the rate of the shear strength reduction increase as the particle roundness increases. So the particle shape and dilatancy are intricately involved, I think. I think still this is under research. So if you want to involve this kind of topics, I encourage you, the student, to come to Kumamoto universities. Okay, the conclusions. So it's a repeat. There is the clear correlation between particle shape, strength, and fracture morphologies. Pumice is a material that is extremely prone to the particle fracturing due to its irregular shape and heterogeneous structures. And in pumice, the shear strength is reduced by the effect of the rotational deformation of the internal particles, which occurs locally in a specimen as a result of the shear deformations. So these are my conclusions. Then, when this is still the laboratory test, then let's assume the mechanism of the landslide in the mountain areas. This orange part is pumice layers. Okay. Then when this this dot line is the original slope line, so the white part should be there. The soil, it's a clay soil. Okay. Then now earthquake come. Then excessive pore pressure increase in the pumice layer. Then some soil start to landsliding. Then some community was damaged by soil. I think this is the story at the Kumamoto earthquake, I think. So that is almost 60 years ago. Then now what's happened? So now it was really renovated, and it's a memorial park. So, now see, this is the after the big earthquake, then you can see the fault. So now this area become the memorial park. So if we have a chance to come to Kumamoto, I can take you to this place. I think this is a good opportunities. Okay, so before I end my presentation, so this is my favorite picture. I really appreciate Dr. Ria. Always she encouraged me to give us a research collaboration, and the Randy, the Mahendra also. And then she's also she came to Kumamoto University as a visiting student. And then she will come to Kumamoto University this year, I think, from this coming October as a double degree program student. So anyway, you have a chance to come to Kumamoto University, many. So I hope we can see at the Kumamoto University. Thank you for your kind attention. Thank you very much.
You could you hear clear voice?
So if you have I will send my presentation slide later. Just I was busy, so I cannot send it to you before. I'm sorry about this, but later I will send it to you. Then you can see some the QR code to check my homepage. I prepared the English homepage so that you can check later. Anyway.
Sensei.
Yes. I cannot hear you, Randy, now.
Because there is a sound system problem.
So.
Please wait for a second. Hello? Hello?
Yeah, now I can hear you.
Okay. Thank you very much for your great explanation, Sensei, about volcanic soil in Kumamoto and how to characterize this soil, especially in the earthquake-prone area. I remember when you invited Mahendra and I to go to also mountain just before earthquake, where there. Okay, now we go to the Q&A session. First, I will question to the. Please put your question. Please mention your name and.
Now someone is talking.
Maybe I will ask you some questions, Sensei, because it's very interesting explanation. You said in the first that the top layer of volcanic ash is red clay and black clay below them, and also from the crushing test shows the bad characteristic as well as the other characteristic. What my question is there any probability of unsaturated soil problem in this volcanic soil, Sensei? And the second question is, how is the stability analysis model of this slope?
Okay, and from the first questions, I think the water ground level is relatively high. So I don't think the unsaturated condition cause some problems. for this case. Yeah. I don't get your second question. Could you tell me again?
Okay, the second is the analysis of this type. Hello? Sensei? How is the stability analysis model of this loop?
I didn't yet. You can do for me. I know that we don't have enough data about the soil strength properties, and also it's quite complicated. So we didn't perform the slope stability analysis yet. Just focusing more on the characteristic part.
Okay.
But you can do. Yeah.
Is there any question from this meeting room? Riasit, to you, Sensei.
Sure.
Welcome you. Thank you very much for your coming. Okay. The Bulmis soil. Is it not clay shell?
What is it?
It is not clay shell.
Yeah, partially clay, but mostly sand, I think. And also the particle involve the water. If this is a pure sand, the moisture content is not so high. So this is the interesting point. The distribution curve is like a sandy soil, but each particle has a porous part inside. That's why each particle can hold the water. That's why the moisture content is relatively higher than sand. So that's an issue. Interesting issue.
So this correlation between the increase of the water content and the increase in the shear strength.
So strictly speaking, we didn't perform the triaxial compression test. So this means I cannot evaluate the pore pressure. This time is just, we apply the only direct shear test. So in this case, I evaluate the total stress. I don't evaluate the effective stress yet. So I think if permeable soil involves the water, excessive water pressure should be increased. So that means effective stress should be decreased, right? So the shear stress should be decreased. So when earthquake happened, shear stress reduced because of excessive pore pressure increase. That excessive pore pressure comes from where? Water in a particle. That is my assumption.
There must be another dissertation for that, another graduate students to overcome this problem.
Yeah.
Yeah. Okay, then we can discuss a bit deeper when we can discuss that.
Yeah. Please come.
Thank you.
Yep. You're most welcome. All the time.
Thank you. Is there any question from this group? Yeah.
Hello, sir. I am Prof, a student. ITS. I assume from your presentation, the PAMIS layer is not in the surface layer. So how to identify that layer is a PAMIS? And what is the solution if in our construction we find a layer of PAMIS? Thank you.
So your question is, when you discover the PAMIS layer in the soil, then what's kind of the countermeasure we have? That is your question?
Yes.
So that case, we should install the deep foundation, like a pipe. You know, the PAMIS layer is a kind of the unstable layers. So that means we shouldn't load on the PAMIS layers. But if you want to develop the structure, yes, you need to install the deep foundations, like a pipe. Then you can penetrate the PAMIS layers. Do you get my point?
Yes, I get your point. And how to identify that in existing we got the PAMIS layer? Is it enough with the soil investigation or any other to identify that is the PAMIS layer?
Could you explain again?
If we have a construction in the PAMIS layer before we start the construction, is it enough if just with the soil investigation to get there is a PAMIS layer?
Yeah. So I think that if you have some information about the PAMIS, so I think strongly we encourage you to perform the soil investigations to check where is the PAMIS layers. 10 meter, 15 meter, maybe no good. So in that case, we need to install the deep foundations. But if 20 meter, 30 meter, in that case, maybe okay. But it's depend on what kind of the size of the structure you will develop. So always I encourage to check the soil investigations. So this case, you know, there are not enough investigation data. As I show you in the pictures, there is the observatory laboratory of the Kyoto universities. When they developed that buildings, they did only 2 soil investigations, only 2 points. So that's why not so many informations. But this time, just we recognize, oh my God, lots of the PAMIS here. So if we know before, maybe we can do something to the community to avoid this kind of the situations, I think. So that's why I'm going to encourage you to check, to do the soil investigation before, of course.
Right. Can you hear my voice, Sensei?
Yes.
Okay. Maybe I will continue the question. Is there any special investigation that we should do before the construction begin? I mean, the special investigation for knowing the PAMIS layer.
That's
kind of the test.
Tough questions. You know that if PAMIS layer exists, the shallow part, the radar scanner can recognize. Radar scanner. But you know the still radar scanner is the resolution not so high that someone is calling me. Just a second. Now it's cut. Oh my God. Okay. So that I think the physical what detector not detector. How can I say? Like physical scanners. So that you know, radar scanner, not laser, radar. Radar scanner can detect the like a big hole or like a water layer under the until 5 meters is okay. Better resolutions, but more than 5 meters, that's still not good enough resolution, I think. Especially the
Please continue.
yeah, so that if the pumice layer has lots of water, maybe the resistivity tomography can detect something. But I think still under the research. But you know, this is the kind of that we need to break through somehow, because nowadays we have drone. We can scan wide area by drone. You know, not only sky, but also the water, right? Sea, pond, river. As long as you have a water drone, you can investigate the inside, but only soil is different. Very difficult, right? To on the inside. So I think somehow we really need to develop the new technology to scan the inside of the soil. Of course, X-ray CT scanner can scan the soil material, but not in situ conditions. Only soil sample. So this is the issue. So I really hope to get the new technology. Okay.
So the first step to investigate radar or resistivity and so on.
Right.
Okay. There is the last question from the online Zoom, Sensei.
Okay.
From Mr. Gadjah. The question is, what is the porosity of the pumice soil? Observing the behavior of the pumice soil, is it similar to unstable group weakly cemented soil, which will collect
I guess he talking about this table.
Yeah, actually the characteristic of the pumice soil, the porosity and so on.
You know, it is not so easy to get the porosity from the conventional soil mechanics, because in conventional soil mechanics can evaluate the porosity for the soil in dense conditions, but the pumice soil involved the porous in the particles, so that not so easy to get the porosity correctly. So I cannot say how much the difference, the porosity between the pumice and the conventional soil. But apparently pumice soil is a higher porosity. But you know, the definition of the porosity should be between particle and the particle, not inside of the particle, right? Do you get my point? So I think that, if I can check it, I can let you know later through the Dr. Satoriya. Okay?
All right, thank you. But the second question from the online Zoom, is there any difference with the weakly cemented layer?
Sorry?
Is there any difference with the weakly cemented soil compared to the pumice soil? Is there any difference with the weakly cemented soil? Basic that distinguish among them?
Yeah, like a color is a kind of the feature. So the pumice soil is like orange here.
Oh.
It's pretty orange. Yeah, pretty orange. And also when you have it, then it's pretty juicy. When you crush the small road from the pumice, we can observe the water from the pumice soil. So that's why I said the pumice particle have the porous condition in the particle with water. That's why water comes from the particle. But the other soil is not like that.
As you said, like cheese in the image analysis, like cheese. Is that right? Cheese. You eat cheese.
can you send it to me? Can you send it to me the chat? Cheese.
No. I just said to you that you in the first slide you said that the structure of the pumice soil is like a cheese with a lot of pore distribution.
Yeah, cheese. Yes. Right. Yes, cheese.
All right. I think the time is already running out, Sensei. Actually, there is a lot of questions in the both of YouTube and Zoom meeting. And I will end the session. And we are asking
Randy.
if there is maybe.
Randy.
Yes, Sensei.
There are one more thing. So the one student said the landslide due to liquefaction. So is that the landslide due to liquefaction? One student asking me. Yes, partially. Liquefaction is used for the sandy soil, but the pumice soil is sand and clay, like a very mixed soil. So I cannot say this is the completely liquefactions, but partially like that. So that this landslide has happened partially kinds of the liquefactions. So this is my answer. Okay, thank you.
Okay, thank you, Sensei. For we know that your time is very limited. So also we are asking our apology if there is mistake during this lecture. Once again, thank you very much, Sensei. Please give a big applause for Professor Toshifumi.
Thank you very much.
And could we take a photo together with Ria Sensei and Endra? Sensei, could you please to pin in out our picture?
Sure.
And Ria Sensei. One, two, three. Once again, 1, 2, 3. Thank you very much, Sensei, for your.
Terima kasih.
Terima kasih. Sama-sama.
Sama-sama. Yes. Terima kasih. Sama-sama.
Bye-bye, Sensei.
Okay. So I have a class. I have to go. So see you soon. Okay. Thank you very much.
Thank you.
Okay.
Baik, untuk sesi selanjutnya saya kembalikan ke MC. Terima kasih.
Terima kasih atas penyampaian materinya dari Profesor Mukunoki dan Bapak Ibu moderator. Untuk sesi ketiga akan saya serahkan ke moderator kepada Pak Andi. Saya persilakan.
Baik, mohon izin kami lanjutkan untuk sesi pembicara utama yang pertama dari perguruan tinggi dalam negeri. Jadi kami sudah lalui adalah pembicara dari perguruan tinggi luar negeri. Sekarang adalah pembicara utama dari perguruan tinggi dalam negeri yang akan dibawakan oleh Bapak Endra Susila, STMD PhD dari Institut Teknologi Bandung, Bapak Endra Susila, apakah sudah hadir? Selamat pagi, Pak.
Ya, sudah standby.
Baik, terima kasih Pak Endra. Izinkan saya untuk membacakan CV singkat beliau. Bapak Endra Susila PhD, PI, Senior Technical Engineering. Beliau berdiri, kemudian untuk riwayat pendidikan, PhD-nya di University of Michigan, USA tahun 2005. Dan untuk posisi sekarang adalah dosen di Faculty of Civil and Environmental Engineering ITB, dan beliau juga member of tim ahli bangunan gedung di Jakarta dan Bandung, dan beliau juga sebagai salah satu principal engineer di ITB. Dan beliau kebetulan adalah kepala departemen teknik sipil di ITB. Baik, untuk mempersingkat waktu dan tempat, kami persilakan kepada Bapak Endra Susila. Kira-kira waktu kami berikan kurang lebih adalah 1 jam.